Right. Okay, in the first lecture, we were just looking at lines. Okay, straight lines. We also want to be able to draw circles. So lines and circles are the key. Okay, so we're going in the second half of the lecture, we're going to be looking at drawing circles. Now, the good thing about circles is they're symmetrical. They have lots and lots of lines of symmetry. Okay, so if you check out this diagram. Okay, what we have here is what we do with our circle line drawings. We start at the 12 o'clock position. So let's say I wanted to draw this circle. We could start at the 12 o'clock position, and for any point along the circle around to the line y equals x, I automatically know the points of 7 other corresponding points on the circle. So for example, if I know what x and y are, okay, I also know that yx is on the circle. I also know that y minus x is there, and x minus y, etc. So just by knowing one point, I know 8 points, just by combinations of x and y, and plus x and minus y. And that's what we call circle symmetry. So if we want to draw a circle, we don't have to go all the way around the circle. We just have to go 1/8 of the way around. Then all the other coordinates can be found by simply x and y, y and x, and negative. Okay, so combinations of positive and negative x and y's. So that's the first thing we do. So immediately, if we use circle symmetry, we cut down on the amount of work we do by sort of 7/8. If you wanted to use MATLAB code, which you will do because it's part of your assignment, this is a function, quite a simple function, and what this does is it invokes circle symmetry. So if you're given a raster, x and y, those are coordinates of a point on the circle. C is the center coordinates of your circle, and color is whatever color you want to draw the circle in. What this does is it plots or fills in the raster of those 8 points around the circle. So just using combinations of x, y, plus x minus x, etc. Okay, so that's the MATLAB code. Right, so that's circle symmetry. We still got to calculate the pixels in the first quadrant. That's the quadrant going from the 12 o'clock position to about the 1/2 position, i.e. at the 45-degree angle line. And we use a method called the midpoint algorithm. Now, this is exactly the same as Gresham's algorithm in its sort of approach. So you're calculating an error. If the error is positive, you illuminate 1 pixel. If it's negative, you illuminate the other. It's called the midpoint algorithm because the error is between the midpoint between 2 pixels. Okay, so let's say we've already illuminated pixel xy, which is this one here. Okay, if we go across, we've got the choice between the pixel to the east and the pixel to the southeast. Okay, so because we're starting at the 12 o'clock position, we're going sort of down to the left and down. But how far to the right and down? Sorry, how far down we need to go is determined by which pixel. So we've got a choice between 2. Okay, and what we do is we calculate the error between the midpoint between the 2 pixels we're trying to decide upon, and then we use the sign of that error to choose. So the midpoint is actually at y minus 1/2. So if there's a 1, if the distance between these 2 coordinates is 1, obviously the midpoint will be 1/2. So this is the midpoint is at y minus 1/2. And instead of a line where we use an equation of a line, for circles we use an equation of a circle, which is x squared plus y squared equals r squared. That's essentially Pythagoras, if you think about it. Okay. So there's a circle centered at the origin with radius r. A point on the circle, it satisfies this equation. So if I rearrange this quite simply by subtracting r squared from both sides, I have this expression here, which is the error between any point, the point xy, and the circle. Okay, so that's our error. So what we do is we use a very similar approach to Brescian's algorithm. Okay, so we use the value of the error. If it's positive, we illuminate the pixel to the east. If it's negative, we illuminate the pixel to the southeast. Okay, and the error is calculated at the difference between the idealized circle and the midpoint between two pixels. Start at the 12 o'clock position, so that has coordinates 0 and r. So we are assuming that our circle is centered at 0, 0. That's not going to be the case, but we just add the center coordinates to it just to translate it. We continue until x is equal to y, and we use circle symmetry to determine the pixels in the other 7 octants. And we want all calculations to use integers. We don't want to have to mess about with real numbers. So it's similar to Brescian's algorithm. Okay, so like Brescian's algorithm, we need a change in error. Okay, so if we've got an error value, which is epsilon, we need to change an error. And what we do is we calculate the error at midpoints between two sets of pixels. The first set of pixels are the ones just to the right, so the ones at x plus 1. And we also have a midpoint at 2 pixels time, okay, or at x plus 2. So the midpoint at the pixel between the pixels to the right is at x plus 1, y minus a half. And then if we look at the pixels to the right of that, we're at x plus 2, y I plus 1 minus a half. So we don't know what this y I plus 1 is. It's dependent on which one we choose. So if you put these two sets of coordinates into this error function here, x squared plus y squared minus r squared, okay, so you'll have x squared plus y squared minus r squared, and that's x squared, that's y, well, there should be a squared there, minus r squared. Okay. Quite a lot of expanding out. You've got quite a few quadratics and what have you. Lots of algebra, but it expands out and it simplifies eventually to that. Okay. So 2x plus 3 plus yi plus 1 squared minus yi plus 1 minus y squared plus y. We don't know what this subscript I plus 1 is yet. Okay, that's dependent upon our choice. So if we choose the pixel to the east, so let's say the error was positive, so we go to the east. Okay, our new y coordinate is simply the same as our current y coordinate. Okay, and so our change in error simply becomes 2x plus 3. If, however, we've gone to the southeast, our new y coordinate is our current y coordinate minus 1. Okay, so if we put in y minus 1 in place of this yi plus 1 and that yi plus 1, okay, and we simplify, we get 2x plus 2y plus 5. So those are two expressions for the change in error, depending on which pixel we've chosen. Okay, what about the initial error? Okay, so we need this starting error. Okay, well, it's a difference between the pixel at the 12 o'clock position, which is 0r, and the midpoint between the 2 pixels to the right. So the x coordinate at that point would be 1, and we'd have r minus a half. That would be the midpoint. Okay, plug them into the error formula. Okay, and rearrange to get 5/4 minus r. So that's our initial error. we've got a problem. Okay, what's the problem with this error? What's 5/4 equal to? 5 divided by 4? 1 1/4, 1.25? That's not an integer. So we want only integer only expressions. So if I go back to here, both of these, 2x plus 3 is going to be an integer because x has to be an integer. 2x plus 2y plus 5 is going to be an integer. But unfortunately, our initial value for our error is not an integer. Okay. Fortunately, all we have to do is make this an integer is multiply by 4. If I multiply 5/4 by 4, I get 5, and multiply r by 4, and I get 4r. So all we do, so these are our error expressions. That's our initial error, 5/4 minus r. This is the error, the change in error if we had chosen the east pixel. That's a change in error if I chosen the southeast pixel. Okay. Multiply all of those by 4, we get only integer only expressions. Okay, so all of those multiplied by 4, these are our expressions. Okay, so that's a midpoint algorithm. Okay, so we start off, okay, inputs into our algorithm, we need the raster array, you need the center of the circle, so called Cx and Cy, and the radius. Okay, that's all the information I need to draw a circle. So imagine if you use Paint or any of those paint programs and you click on the circle tool, you can then click on the center of the circle, then you say, okay, I want it to be this wide. This is what that paint program is using. So we start off, we assume that x is 0. We say our y coordinate is going to be the radius, that's at the top, the 12 o'clock position, and our initial error is 5 minus 4r. Whilst x is less than or equal to y, so that's in that first octant, sort of 12 o'clock to sort of 1/2, we use circle symmetry. So we've got the center, we've got the x and y coordinates, all the combinations, there are 8 of them. We use circle symmetry to illuminate all those points. If the error was negative, okay, you update it. You go to the east and update it. If the error was positive, you go to the southeast, update the error, and go to the pixel below. So it's -1 from y. Okay, and you continue until you've got a circle. Okay, if you prefer, I think in the notes again, I've used the flow diagram for that. Just some people prefer flow diagram, some people prefer sort of algorithms. It's the same thing, really. Okay, and that's what you get. Okay, so what I've done there is just what have I got? I've got 100 by 100 raster array, and I draw various circles of different radii, and you can see they look like circles. Remember, this is quite a low resolution array. 100 by 100 is not very high res, so it does look sort of jaggedy. If you had it on a higher res, it would look a lot better. So it just happens to be jaggedy. Okay, so what I want you to do now, get it right, yeah, is turn to the last page of your the last page of the activity sheet, and I want you to draw a circle. Okay, it's a bit of a bigger raster, just so I can sort of get a meaningful circle going. Okay, so this is the final activity. Using the midpoint algorithm and circle symmetry, draw a circle centered at the pixel 1010. So where's 1010? So that's going to be 1010. That one there. I'm just going to put a little cross there, just there. Okay, that's the centre of the circle. With a radius of 9 on the axis below. Okay. So to start with, okay, we've got to initialize. We're starting at x equals 0, y. Well, that's going to be equal to r. But actually, I might as well sort of do it from the raster coordinates. So if it's radius 9, we've got 1, 2, 3, 4, 7, 8, 9. Okay, so x is 0, y is 9. Okay, our error is going to be 5 minus 4 times r. So 4 times 9 is 36, minus 5 minus 36, minus 31. Okay. Right, so I'm going to illuminate the one at 12 o'clock position, but using symmetry. Okay. So if I sort of use symmetry, I'm also going to illuminate the one 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to illuminate that one. So that's at 0, 9, or 0 centre plus 9. This one's at 0 centre minus 9. I'm also going to have one here. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's that one. And going the other way, I'm going to have that one there. So for the first pixel, rather than illuminating 8, we can only illuminate 4. Because remember, we're dealing with whole pixels here. Okay, so our centre has to be on the pixel. Okay, well, our error is minus 31, which is less than 0. Therefore, we go to the east pixel. So our next pixel is going to be x equals 1, y equals 9. So we've just gone straight across to the east. Okay, so we were here, and I'm going to go to the east. So we've got that pixel. Now we can invoke symmetry. So if I went to the east from that one, I could also go to the west. So I'm filling out that one. Likewise down here. If I invoke all my symmetry, okay, and over here as well. And over here. So just by calculating one of them, I can then calculate 7 others. Right, now I have to calculate what my error is. So my current error is 31. Now, if we went to the east, we add 8 times our x coordinate minus 8 times our x coordinate plus 12. So our x coordinate is 1 plus 12. So essentially I'm going to add 20 to my current error. So that's 8 times our x coordinate, which is 1 plus 12. So actually, sorry, hang on a sec, I should have done that before. Sorry, I should have done that on this. I'm just looking through the algorithm. You calculate the error before moving. Yeah, sorry, I should have done that here. So our current error is minus 31. And I add 8 times 0. So that's 8 times 0 and then plus 12 to it. So essentially it's minus 31 add 12, which is minus 19. Okay, sorry about that. Doesn't change what we illuminated. Okay, so it doesn't change. We go to the east, that's right. Okay, our error is equal to minus 19, which is again less than 0. So we go to the east again. Okay, and calculate the new error, which is minus 19 plus 8 times 1 plus 12. That'll be 1. So now we've gone to the east again. Okay, so we're here now. So go all the way around. So it looks like you're just doing 4 squares and 4 lines at the moment. But in a minute, you'll see start sort of going inwards. Okay. Now our error is 1, which is greater than 0, so therefore we go to the southeast this time. Okay, so we go to the southeast. So what we change our error by is 8 times x minus 8 times y plus 25. It should be plus 20 actually. Sorry. So we have 8 times x, which is 2, minus 8 times y, which is 9, plus 20. So 8 times 2 is, so what we've got? 1 plus 16, 17, minus 72. Oh dear. What's 17 minus 72? Anyone? Well, 72 minus 17 is 50.
Minus 35.
So?
I think it's minus 35.
Yes.
Minus 35.
35 plus 20.
Oh, no, like,
Oh, the whole thing. Thank you. Okay, so we're minus 35. Okay, so we had to go to the southeast. So x equals 3. This time y is equal to 8, because we've gone down 1. Okay, so we have that one there. So if you think about it, mirror image around that line. Oh, we haven't done that one yet, have we? Yes. Yeah, so we go to there. Now we do the same all the way around. Getting a bit lazy with my shading. You can do it neater than me. Okay, so our error is now minus 35. So it's less than 0, so therefore we just go to the east pixel. And to this, we add 8x plus 12. So now we've got 8 times 3 plus 12. So 8 3 is 24, plus 12 is 36. So we've got 1. Okay, so that time we get east pixel, which is at x equals 4, y equals 8. So it's that one. Okay, and again using symmetry, just imagine there's sort of like 4 mirrors on here. You can start to see we're sort of enclosing in the circle. Okay, so the error this time is 1, which is positive. They therefore go to the southeast on the next pixel. But we have to change the error. So we have 1, and this time it's plus 8 times the x coordinate, which is 4, minus 8 times the y coordinate, 8 plus 20. We've got another one of these. So we have 1 plus 32, which is 33, minus 64, that minus 31, plus 20, It's minus 11. Is that right? So 32 minus 64 is minus 32, isn't it? Plus 20 will be minus 12. So 1 minus 12 is minus 11. This pixel, we're at x equals 5, y equals 7. That pixel there. Okay. And if you again use symmetry, all the way around, you can see we're almost done. Okay, so our error is now minus 11, which is negative, so we continue to the east. And we update the error, minus 11 plus 8 times x, so that's 8 times 5, plus 12. So 8 5s are 40, plus 12 is 52, minus 11 is 43, so 41. Okay, so if we go to the east, we have x equals 6, y equals 7. So that one there. Correct. East. Okay, so if we continue to do the symmetry all the way around, you can see that we've now got it joined up. We could, I mean, it could continue, but you only be shading pixels twice. Okay, so you can see you've now got a circle. Sort of, it does look a bit jaggedy, I admit. It is a low res, it's quite a low sort of resolution raster. But you can see by using the midpoint algorithm, we can go around using symmetry and draw the circle. Okay. It can be a little bit tedious doing these in this way. But what helps to do it in this way is when you're coding it up, it helps to sort of understand the steps. Okay, so. Okay. Okay, so that was what we had. So we had, I wasn't sure that many people would have compasses to actually draw a circle. So if you were to draw a circle, this is what it would look like. So this black line is the idealized image. And if I just overlay what we just calculated, you can see that the closest pixel to our idealized image is always illuminated. So that's a midpoint method. Okay. Just to go back to the Moodle. Okay, where is it? Your assignment. Go all the way down to assignment 10. Yeah. So part of your assignment, the additional problem, question 2. Amend the MATLAB program so that it draws a circle. So you're going to have to write code to do the midpoint method. Okay, and then you can draw a circle on the outside. So it looks like a pentagram. Okay, so you can see that this is a 200 by 200, and you can see we have a circle around it. So that's the next part. Okay, final thing which we're going to finish up with. Bear in mind, what I'm going to say now with ellipses is not part of your assignment. Okay, so it's slightly more involved, it's slightly more complicated, but it's still, the mathematics is still similar. Okay, this is an ellipse. It's essentially a squashed circle. So instead of having every point on the circle being equal distance away from the center, with the ellipse you have what we call 2 radii. Okay, so you have a minor radius, which is B, and you have a major radius, which is A. Okay. For the purposes of drawing an ellipse, we split the ellipse into two regions, region 1 and region 2. Okay. Region 1 is where the gradient around your ellipse is greater than -1. So you think -1, from your point of view, is like that. So -1, like that. So where you have a gradient of greater than -1, so it's shallower than -1, we're in region 1. The crossover point to region 2 is where our gradient becomes steep. And that's when it's less than -1. So we have two regions. We'll have different calculations for both regions. Okay. Ellipse only has four-way symmetry. Okay, so what if you know x and y, you only know three other points, x and y. Okay, so very similar to circle symmetry, except we can only draw 4 pixels rather than 8. Okay. Now, what we're going to do, we're going to do a midpoint algorithm method for each region, because we're going to have to swap driving axes halfway through. So for region 1, we use x as our driving axis. So we're adding 1 to x each time, working out which y coordinate or which pixel we do. In region 2, you subtract 1 from y each time to work out between two pixels side by side. Okay. Cartesian equation of ellipse is like this. So remember, B is your minor axis, minor radius. So it's b squared x squared plus a squared y squared. Now A is your major radio, and that's equal to a squared b squared. So that's just the equation of ellipse. If you rearrange to make y the subject, you get y in terms of a, b, and x. Now the boundary between region 1 and 2 is where the gradient on our ellipse is equal to -1. So we need to work out where that is. Okay, so we need to use a bit of calculus. Okay, so I'll split it up here. So that's our y in terms of x, a, b, and x. So I've just written it instead of square root, I've got power of half. Instead of divided by a, I've got a to the -1, just to make the differentiation easier. Okay, using the product rule, using chain rule. Okay, dy dx comes out with minus bx over a times root a squared minus x squared. That's just chain rule. It's got a function within a function. So if you let u be a squared minus x squared, this becomes b u to the power half a minus 1, and then that comes out using chain rule. Now we want to know where that point is equal to -1. What's the x coordinate where the gradient is equal to -1? Okay, so we set it equal to -1 and rearrange and solve. So we square both sides to get rid of the square root. Okay, so the -1 becomes 1. This minus disappears and we square in everything. Okay, multiply throughout by the quotient, by the denominator. Okay, factorize in terms of x squared, and then take it back, make x a subject, and you have an expression for x. This expression for x is only in terms of a and b. Okay, so this can be used to determine where region 1 finishes and region 2 begins. So whilst our x coordinate is less than this, we're in region 1. As soon as our x coordinate is greater than that, we're now in region 2. Okay, so we proceed as we did with the midpoint algorithm. So we're taking the equation of an ellipse. If the ellipse starts at 0b, which is kind of like the 12 o'clock position on the ellipse, okay, the initial error is going to be the error at the midpoint between the 2 pixels to the east. So pixel to the east, pixel to the southeast, minus the error at the 12 o'clock position. Okay, so if you plug them into this formula, rearrange, simplify, that's your initial error. Okay. What I've done, I've called this epsilon sort of I, comma 0. So that's the initial error for region 1 or region I. Okay, change an error, again the same method. Take the midpoints between the pixel to the right and the pixel to the right of that, subtract them. Okay, a bit of algebra is sort of so you get down to this expression. If the pixel to the east was chosen, our y coordinate doesn't change. Okay, so the change in error just becomes this. And if the pixel to the southeast was chosen, our y coordinate is subtracted, well, we subtract 1 from it. And that's our change in error for region 1 if we chosen the southeast coordinate. In region 2, okay, so region 1 we go across and then work out whether we go down or not. In region 2 we go down and work out whether we go across or not. Because we've flipped it now, we're using y as a driving axis. Okay, so what I mean by this is we've just illuminated this pixel, this one here. We've got to choose between these two. So we've got to choose whether we go south or southeast. Okay, and again we use exactly the same method. Okay, the midpoint is x plus a half this time. Okay, so our change in error, again using exactly the same sort of method, just a bit of algebra. Okay, if we chosen the pixel to the south, there's no change in our x coordinate, so our change in error is this expression. If we've gone to the southeast, then we add 1 to our x coordinate because we've gone across a bit, and that's our change in error. So we have for both regions we have initial error and change in error depending on which pixel we've chosen. Okay, so that's the expressions for region 1 and for region 2. Okay, and so you pretty much exactly the same. Okay, you do that, and you can draw ellipses. So note when A and B are the same, it defaults back to the midpoint algorithm. So if A and B were identical, it becomes a midpoint algorithm. So when when you're doing your sort of drawing packages or you're doing paint or something like that, and you choose the ellipse tool or you choose the circle tool, it's doing the midpoint algorithm. That's how it's drawing your circles and your ellipses. Okay, so that's pretty much what I wanted to cover today. Rasterizing of lines. Just to remind you, your assignment 10 is drawing that sort of pentagram thing. I didn't intend it to be a pentagram; it just sort of happened like that. Okay, so problem 1 is drawing the star. The additional problem 2 is drawing the circle. Additional problem 3 is drawing your village or your virtual world using rasters. Okay, so that's quite tricky, that final one. Okay, if you've got any questions about any of the assignments over here, if not, I'll see you all in the lab next week.
You know in assignment 6 when it says change it so it goes
Yeah.
I've changed the storing of the hit thing into an array, but I don't know how to call on the array in that if loop. Would I change it from an if loop to because it's not an if, it's an and.
So what you can do is start off by drawing every polygon, and then loop through your array where the polygons are hit, and do them separately. So if you've got a list say it's 4, you should have polygon number associated with each cell. So you just say, okay, that's polygon 5. Okay, I'm going to draw that red, like that. So loop through it separately. So you're doing all of them. It seems that you're doing everyone, and then after that, then only loop for the ones which you pick.
Yeah. Because if you can't really do that if loop with the else if though, so then that would, if it went through the loop and then did the else if and white if.
You wouldn't know. Also, you wouldn't know how many.
Yeah.
Whether it's, you could be at a given polygon, but you don't know whether it's gone through any more.
Yeah. What I did with like the way I stored it though, it did work because I was using this commands after it just to like visualize it better, and it. I don't know. I just couldn't. I'll have to show it.
I was going to say without seeing your code.
Yeah. I'll work on it.
Oh, you need a spare one? Did you not have one?
No, it's not.
I haven't got to check my phone at night.
Yeah. That's an easy one to check. Do you have this? Actually, I've got it here. Is it showing up there? Yeah. Right, this is how I mark these. Trying to see where actually. I can tell. So ITE. So I know you cut down ITE. FGH is front. KRBC behind. Your next cut was MPX. So NO behind. BY in front. In front of BY is W. Where's L? L. So you cut down BY. So you've done MPX. So you've got all this in front. So you got across BY, you got LQW.
Yeah, I wasn't sure if you could.
Yeah. Well, the Q faces away from W, so you need another cut. If you see here, right, Q's facing up, W's facing down, so they're facing away. So you need another cut. So BY, behind BY is AZ, that's right. But in front of BY will be L, Q, and W.
Okay, that's quite easy to.
Yeah, you just do either across Q or across W. You know, it doesn't matter which one.
Right.
Yeah. But you'll have another one there. With JSUD, you got S facing up and U facing down. So you need another cut.
Right.
Imagine nothing else exists apart from those four JSUD. So you need to cut either along S or along U.
Right. Cause I assumed I thought they'd just be separate. I didn't realise it's sort of.
Yeah, it extends forever unless you cut it.
Okay.
Yeah, so I mean that
I need to cut one of them as well. So I basically need to add another cut to
cut and then you're missing an L.
Yeah.
Yeah. Another cut.
So would that affect my?
That'll affect 3.
Okay.
So 3 would be needed to do again.
Yeah,
2
it's not too different.
2 won't be needed to do again because it's using this one here. Oops, sorry, it's wrong. Right, so you start at HP. It's back, so go to FR. FR is front, so go BV. B is front, so go AW, BV. And then you got, and then DT is back, so you go front, so you got CU now.
That's what I didn't know what to do because
you're right. AW is correct. That's first one.
Because normally you go up and then back up, so I just sort of.
You only go back up if it's a leaf node.
Right. Okay.
Yeah. So you go AW, BV, and then you look at this one. You say, okay, DT is back facing, so we go to CU. So CU is a leaf node, so add it. And followed by the parent,
and then
that one. That happens to be a leaf node. So then you do that, add that one. You try and add that, but you can't, because it's already been added. Try and add that, it's been added, so then you're up there.
GQ, HP.
Yeah, and then you look at JN. J is back facing, so go KLM.
Yeah, JN.
Yeah.
Okay, that's fine. Okay. So it's just a couple of things.
Oh yeah, only that's quite a good assignment. Now it's a nice.
Yeah.
It's a nice sort of like, okay, you've been doing MATLAB and all that stuff for a while now. It's a nice sort of quick one to get at. You've aged a lot in the last week.
That coursework, it number theory messed me up.
Yeah. Have you had feedback from the number theory yet?
No, I don't think we have that yet.
It's just that last question, I just left it. With this one, I've kind of forgotten how to do it. I did it in the lecture last week.
Yeah. So for the first one, remember you got to cut. You got to insert hyperplanes along.
Yeah.
And what you do is, if you have any polygons which are in front of your cut, list in the left child node.
Right. And do you choose which way is the front? or not?
No, assume that all of these are inward facing. So imagine this is like this is like a corridor, and then you're walking around
Yeah.
here. All of these will be facing with
Well,
inwards.
inside, yeah. Okay.
So it's just like it's
So
how,
if I cut ITE,
yeah. If you did
straight
IT as
down.
your first cut, HGF.
a front facing,
Yes.
and all of these are back facing.
Yes.
And then that would be my cut at the top. Like,
Yes.
if you scroll down a little bit.
That would be your root
So that
node.
would be my ITE.
Yeah. Yeah.
And then all these would be back here. You do
Yes.
the same thing.
Yeah.
And,
But with the FGH, they're all facing each other.
yeah.
Think of these. Think of if they were, they can all see each other. If they can all face each other, they're convex, so you don't have to split them up.
And that's the circle.
Yes.
And then if they're not, use the square.
Yes. We don't have to do that, but that's what I do. It just keeps track of what you
What
need
you need to
split
sort
up.
out.
Isn't it, how do we need to do this on the LaTeX?
You can do it, right? On LaTeX, the easiest. Oh, wrong one. I forget you can see that. What I've done on LaTeX is Killian's picture. Where has it gone? Oh well. Go back to Moodle. How to draw trees in LaTeX. Right. Right. There's a package called ticks. Okay. So if you copy and paste that into your top of your LaTeX, where you want to draw a tree, this is how. I mean, this tree here is drawn using this. So there's your root node. So a child node of the root node is DE, and a child node of DE is HI and JK, and another child node of ABC is FG. That's the easiest way I found to do it. And you might have to change these around, sibling distances. These are the distance between, like DE and FG would be 6 centimeters apart.
Yeah, that's easy enough.
Yeah, I mean that's on Moodle now. So.
Yeah.
Yeah. It beats sort of using paint or something just to try and do it.
Yeah.
All right. See you next week.